Guys, today we're going to be looking at how we measure evolution. So thus far we've looked at kind of an introduction piece to evolution. We looked at mechanisms, 5 different mechanisms of evolutionary change. So today we're going to look at how we measure evolution, or how we could measure this perhaps in the field. So again, we're going to be looking at measuring evolution. We're looking at measuring evolution. So essentially, to do this, we use a set of equations, right? And they are called the Hardy-Weinberg equilibrium equation. So we're going to use this Hardy-Weinberg equilibrium equation to calculate allele frequencies. Or percentages. You can think of them as just percentages. And we do this, we're going to use these things to determine if a population is evolving or at what we would call equilibrium. So we're going to use this equation set to determine if our population is evolving or if it's at equilibrium. So here's the two equations. Again, we've defined evolution as just a change in allele frequencies over time. So our equations are these: P plus Q equals 1. And P and Q, those are allele frequencies. And then our other equation is P squared plus 2PQ plus Q squared equals 1. And these are population genotype frequencies. So we have allele frequencies and we have population genotype frequencies. So let's use an example. So here I've got some beetles. And these beetles, in reality, you would not be able to see these genotypes. You wouldn't know what these genotypes are. You wouldn't know if this beetle is big A or big A little a. They would all just look dark to you. And then these beetles would all be light colored or tan, but you would know they're little a because of the way that this allele is being inherited, and that the dominant version produces this darker pigmentation in the beetle, and the recessive version, if they're both there, produces this lighter pigmentation in the beetle. So again, we would know that these light colored beetles must be little a, but we wouldn't know if this one is big A or big A little a. They would just like look like dark beetles. So there has to be a way that we can somewhat project and predict these allele frequencies. Allele frequencies would be the total number of capital A's that I have in the gene pool on the page. And then the other allele frequency would be the total number of little a's that I have on the page. Genotype frequencies would be how many big A homozygous dominant beetles do I have. That'd be P squared. Q squared would be the number of homozygous recessive individuals. And then 2PQ would be the number of heterozygous individuals. So again, I'd be able to determine how many homozygous recessive I have because they look different, but it'd be very difficult without some sort of equation set or algorithm to figure out how many look like this in terms of genotype and how many are like this in terms of genotype. So that's what we use the equation for. So you want to start with this Q squared value. That's typically the place that you begin. So Q squared is going to give me the percent or the frequency of homozygous recessive individuals in a population. And in our population of beetles here, it's going to be the individuals that have both little a's. Again, to be this light-colored beetle, you have to have both recessive alleles. Otherwise, you would have the dark shell. So in our beetles, we'll just kind of track this beetle example through. So in our beetle example, if we tally these up, we've got 2, 4, 6, 8, 10, we have 12. We have 12 total beetles that are light colored. And we have a population total of 42. So 12 that are light over the 42 total, right? It's 6 across, 7 down, so that's 42 total beetles. That gives me a percentage of 29% or 0.29 frequency. So that is going to be my Q squared value. That tells me 29% of my beetles are the recessive phenotype or Q squared. So from there, I can do some rearranging. I have Q squared, so I can use that to find Q. All I have to do is square root it. So I'm going to be able to figure out what Q is now. And Q is going to be it's going to be the percentage of A's I have in my gene pool. What percentage of recessive alleles in my gene pool? So it's going to be the percent or the frequency of recessive alleles in a gene pool. And in the case of our example here, it's the percentage of little a alleles. Not how many individuals, but how many alleles. We're looking at the whole gene pool. We're looking at all the letters on this page. We want to know what percentage are little a's. So for the beetle here, we're going to take my Q squared value, which I have from earlier, right? It's 0.29. I'm going to then go ahead and square root that. So Q squared square rooted. That's going to give me Q with a value, if I square root this, of 0.54. 54%. That tells me that we're projecting that 54% of my alleles on this page are little a, or just little a. That means 54% of the letters on this page are little a. I can count them all up, divide by the total number of letters. There's 42 beetles. They each have 2 letters, so there's 84 total letters here. And we're saying that 54% of those 84 should be little a following my equation set. We'll double check and see what that is here in a little bit and see how accurate our equation set is. So I've got Q squared. I have Q. Now I can find P. I just have to rearrange this, move the Q over here, and that'll give me P. So let's go ahead and look at that and do that. So I'm now going to be able to find P. So P is going to represent the percentage or the frequency of dominant alleles. So the big A in this case in a gene pool. Right, so the capital A, so that would be the total percentage of big A's on the page. So again, how I would sort this, I've got my beetle example, and we said that Q from earlier is 0.54. And I know that 1 minus Q equals P, because P plus Q equals 1. So I can just plug in these values. 1 minus 0.54 equals 0.46, 46%. So that's telling me 46% of the letters on this page should be a big A. Now I have P, I can just square it and get P squared. So let's work this through. P squared. That's going to be the percent or the frequency of the homozygous dominant. Individuals. That's big A, big A. So that's going to give me the percentage of individuals that are like this genotype, right? Because P times P, P times P is big A, big A. So let's look at this. Beetle-wise, I'm looking at a p-value from earlier of 0.46. So P squared is going to be 0.46 squared. So P squared is 0.21, 21%. 21% of my beetles should be big A, big A. So last but not least, I've got one last variable to find, and that is 2PQ. So this is going to be the percent or the frequency of the heterozygous, the big A, little a. So this is big A, little a. So 2PQ. So let's go back to the beetles. I've got 2 times my p-value from above is 0.46. My q-value is 0.54 from above. So multiply that together, I get 0.50. 50% of my beetles are projected to be big A, little a. So I got 50% are big A, little a. I've got 21% are big A, big A. And then my Q squared value was 29%. So let's just check our math here. 21 plus 29 plus 50, that's 100. So we're good to go. That math checks out. Or 0.29 plus 0.50 plus 0.21 equals 1. Okay, that's what we're looking at. So that's how you would find these frequencies for any population. Now, what I will tell you is that in smaller populations, sometimes the Hardy-Weinberg equation will give you values that are different than what a small population truly is and will reflect. So, for example, we've got 42 beetles in this population, which is not a very big group, right? It's a super small sample size. So we're going to compare here our calculated values with the Hardy-Weinberg equation, and then we're going to look at what the actual values are and look at the differences between the two. So we said our p-value, our dominant allele frequency was 46% or 0.46. We're saying that is there's 46% of the letters on the page are big A, according to our equation. And our Q value then was 54%. It's just 1 minus this. And we're saying then that would be that 54% of the letters of the page are little a. So let's look at what this actually is in our gene pool here. So I'm going to use, again, these genotypes that I wouldn't really be able to see in the wild because these would look the same, right? Even though they're different genotype, they would look the same. So I wouldn't really have this luxury in the wild, but I'm just going to show you how the equation can be a little bit different. You might get some genetic drift there in terms of the allele frequencies. So I've got, for Q, I've got 12 beetles, 2, 4, 6, 8, 10, 12. I've got 12 beetles that have 2 recessive alleles, right? I've got 12 beetles here, and they each have 2 recessive alleles. So I'm going to take those 12 beetles times their 2 recessive alleles. Again, this is representing little a. Then I'm going to add the 18 individuals here. There's 18 individuals in my set that are big A, little a. So I'm going to add those 18 here, and then they get multiplied by just 1 because they only have 1 recessive allele. And again, Q is the recessive allele. So this would be 18 individuals that have just 1 little a. And I'm trying to figure out what is the percentage of little a's in my total population. So I'm going to divide this value by, I've got 42 beetles. They each have 2 alleles. So when I do this math, Q gives me 0.50. So that is going to be, that tells me that half the alleles on the page are little a. In reality, that means P is also 0.50 and half the alleles on the page are big A. So you can see my equation did not quite give me the actual amount of alleles in terms of the percentage. It was a little bit off, right? We were about 4% off both ways. So if you have a small population size, your Hardy-Weinberg equilibrium will get you close, but there may be some variance there just because of that small population size. So what does this all mean? And why do we even care about this? If you're a biologist and you're in the field, right, and you take some values, let's say I collected these beetles, and I collected these beetles at year 1. So again, I collected these beetles, I ran my Hardy-Weinberg equilibrium values, and at year 1, my p-value was 0.46, and my Q value was 0.54. And again, this represented the dominant allele in the gene pool. This represented the recessive allele in the gene pool. Then I came back, and let's say I came back 10 years later. So 10 years later, and I'm looking, and now my p-value, my dominant allele frequency is 0.7. It's 70%. And then I calculate, obviously Q is going to be the remainder, 30%. So what does this tell me? This tells me that evolution occurred, that allele frequencies have changed. That's the definition of evolution, the change in allele frequencies over time. So if your values differ from year 1 to year 10, or whatever time interval you're looking at, that's evolution, and that's measured evolution. Now, what could cause this? Well, it's everything that we've discussed: natural selection, genetic drift, gene flow, mutation, sexual selection. So what happens if they don't change? So if your values are the same, so we'll say if your values are the same, then you know your population is at equilibrium. And we could then definitively say that, hey, there's no selection happening, no natural selection or no sexual selection. There is no genetic drift. There is no mutation happening. There is no gene flow happening. And we have then essentially random mating occurring. There is no non-random mating, or there's random mating. So we would know that these 5 things, no selection, no genetic drift, no mutation, no gene flow, and then we have random mating occurring. We would say those things must be true for this population if the values are the same from year 1 to year 10. So it gives us a way to measure whether or not evolution is occurring. Okay? That's all for this time. I hope that's helpful. I'll see you next time.